kinematics, right? Kinematics, particle kinematics is just the geometry of motion. Like I've said several times before, I think once we move past kinematics and get into kinetics, I think the class gets a little bit easier because it's very structured. We have a nice, clean plan to follow each one. Every problem falls into the same type of category, right? And as long as you stick to the plan, you're going to be fine. But like I said, there's a little bit of about this part. Okay, it's like, what do I do? Do I take integrals, derivatives, what? Okay, so we were just talking about polar coordinates. What coordinate system do I use, right? So we were looking at polar coordinates. We had this nice little example of a merry-go-round. That'd be a really perfect place. Something where you have a change in radius and an angle changing at the same time. That's where polar coordinates really shine. You have lots of stuff happening, and there's all these different accelerations, right? The different accelerations we talked about last time were, everything in this equation right here. The r double dot minus r omega squared, the r alpha, the 2r dot omega, right? So we got the radial acceleration, the centripetal acceleration, the tangential acceleration, and the Coriolis, right? And so we kind of talked about where all those came from, and made similarities towards, what's the word I'm looking for? No. Analogy, analogous to the merry-go-round. We talked about each one of these accelerations, and these are all real accelerations, right? And those are all happening at the same time. And so you can't really use your intuition too much on these things. You just got to rely on this equation for accelerations. Okay, so we talked about each one of those things, and then talked about converting, and then we did a quick little example, very quick example about things accelerating on a merry-go-round. Right, we'll do this example today, and then we'll finish up the last topic we have in kinematics, which is relative motion. Right, and we kind of briefly discussed this before, but now we're really going to dive in this concept. We're going to use it throughout the whole semester. After this, like I said, we're headed to kinetics, F equals ma, and then we're going to do work energy, and then we're going to do impulse momentum, and then we'll be done with particles, and we'll go into 2D rigid body motion, where things just get a little more complicated. An exam next Friday, right? That's correct? Anybody? I think it's next Friday. So not this week, right? And then we have a big homework assignment this week, and then next week's going to be lighter because you're going to be studying for an exam. The first exam will be one question from kinematics, and then one question from F equals ma. Right, so we'll just kind of keep that on the radar. Okay. All right, let me get here. My notes here. Okay, so let's do this problem. The first problem here. A block in a disk moves radially outward in a slot with a speed of r dot equal to 4t meters per second. Right? The platform rotates at a constant theta dot equal to 6 radians per second, so it's a constant omega. The block starts from rest at the center. So there's this block, right? And that block can move back and forth along this inside that slot, right? And they tell us some things about what its velocity is inside that slot. And it starts out at 0. Okay, so let's just dive in here. Okay. Just to recap, our velocity equation for something in normal, right? This is kind of like a merry-go-round, so you'd want to use polar coordinates, right? You have the radial changing and then omega changing at the same time. So our velocity equation in this, and we're after the velocity and acceleration vectors. R dot in the ER plus R omega in the E theta. Right? So there's going to be an accelerator, or there's going to be a velocity term in the radial direction moving in and out, but then also there's going to be a velocity in the E theta direction because it's spinning with an omega. Right? Our acceleration equation is R double dot minus R omega squared in the ER direction, plus R alpha plus 2R dot omega, the Coriolis, in the E theta direction. Okay, those are all the terms. And so what this problem's going to be is kind of just filling in all those terms, right? Filling in all the known components that we have, right? But that's I kind of like sometimes just to write that down first so I know where I'm headed, okay? They gave us R dot, right? R dot is equal to 4t. So I can calculate R double dot. It's just going to be the derivative of that, which is just going to be 4. So again, I'm just trying to find all those terms that's inside of that. Okay. The omega was also given to us, which is equal to theta dot, which is equal to 6 radians per second. They say that that's constant. It is constant, it's just 6. And so alpha in this case is going to be equal to 0. Okay. Omega is constant. That means there is no angular acceleration. Alpha is just equal to 0. Right? So in that case, we got just about everything. The one thing we don't have is what this radius is. Right? I got R dot, so that'll be taken care of. R double dot taken care of. Omega's taken care of. Alpha's going to 0. R dot we know. Omega we know. 2 we know. Right? What we don't know is what that R is. Right? So we have to figure out what the radius is. And all they tell us, I know what the velocity is. Right? The velocity is 4t. Right? In the radial direction, and I start out at 0, and so then I have to get the radius. Right? And what I got to do is I got to do some integration. Right? Because if they tell me what R dot is, I know that it's the R is equal to 0 at the beginning, and then it's something else later. I can figure that out. So that's not something that's given to us. It just says that it's trying to figure these accelerations, velocities after 1 second. So let's find out what R is. So we need R at t equals 1 second. Right? So what we know is that R dot is equal to 4t, which is equal to dr dt. Right? And then we put all the t's together. 4t dt is equal to dr. I'm going to integrate this. I'm going to integrate this. I'm going from this is 0 to 1 second, and this going from 0 to r. And if we carry out that integral, we get r is equal to 2 meters at t equals 1 second. I mean, this problem's pretty straightforward. Just take some derivatives on our own. Kind of just noticed we were short something. Then we said, well, I used all the information that I have, and I was able to determine what the R is. Now I have all the components. I know everything in that equation above. Now I just go back and put them all in there. Okay, let's go do that. So back to velocity. The velocity was R dot in the ER direction. ER hat direction. Plus R omega in the E theta direction. I just wrote that up above earlier. So R dot is 4t. And it's saying to figure this thing out at 1 second. So V is equal to 4 times 1 second. That's the t. In the ER direction. Plus, we just figured out what R was, which was just 2. Omega was 6. And that's in the E theta direction. And that is my velocity vector. 4 in the ER hat plus 12 in the E theta hat. That's my velocity. Okay. What does the ER and the E theta mean? It just means at any position. Right? Do I care what angle this thing is at? Is it up here? Is it over here? Is it over here? Right? It's moving. I don't really care. I just know that there's a ER going that direction and an E theta going that direction. And then over here, that's the ER, that's the E theta. Right? It's just varying, and it doesn't matter to me. I don't really care where this thing is at in the rotating circle. Right? Okay, that's the velocity. Then we go to acceleration. Again, just go back up to that original equation. A is equal to r double dot minus r omega squared in ER hat plus r alpha plus 2r dot omega the Coriolis in E theta direction. Right? Now we just come back and substitute in everything I know. R double dot, found before, that's 4. Minus R, we figured out to be 2. Omega is 6. And ER hat plus R is 2. Alpha is 0. Plus 2 times R dot was 4t, so that's times 4. T was 1. Omega was 6. And E theta direction. And if you plug everything in there, we get our A vector to be negative 68 in ER direction plus 48 in E theta direction. That was pretty straightforward. Right, with the exception of a little integral in the middle to determine one of those terms. Cool. Questions? Concerns? Last kinematics topic, okay? And that's going to be relative motion. Give you a second to write that down. You guys are having trouble with homeworks and stuff, don't forget the learning center. Right? I think Aiden's sitting in there, nothing to do except to help you guys. That's his whole job. Right? This class is difficult, and you use those resources that the university's thrown towards you. Right? Or swing by and talk to me. Make sure you're staying on top of it. Like I said before, as long as you keep up with class, right, and you're doing your homework, everything's going to be fine. Okay. Just be careful, right? If you're working with groups, right? Just be careful that you're just not copying what some other people doing, or be careful if you have the solutions manual, because you're not going to have that on the exam, right? This is me versus you on the exam, right? And so just make sure you're doing this yourself, right? I know the solution manual is out there. That's fine. I don't care. Just make sure you're using it right. Where students run into problems is they lean on it too heavily, right? They're just like, oh, I think I know how to do this problem. And they're like, oh yeah, that's how I would have done it. And then they try it. Use it right? Like try to do it yourself. And if you can't do it yourself, just peek every once in a while, right? Like, oh, what do I do? And then just a quick little peek, and then shut it down, and then feel guilty about it, and then go on with the rest of it, okay? Like I said, I've taught this long enough to know where students run into problems. Okay. Relative motion. Okay. So we briefly talked about this before, right? We were talking about reference frames and stuff, but this is, we're going to kind of quantify it with some vectors here, right? So this is the example I used at the beginning of class. If I'm interested in the velocity of that frisbee, for instance, like how fast is it going? Well, am I talking is it how fast is it going relative to the plane, or am I talking about how fast is it going relative to the ground, right? Or am I talking about how fast is it relative to the sun, right? What we pick as being a relative motion point is going to have a huge effect on the answer that we get, okay? And so how do we quantify it? Say if I was on Earth and I was looking up at that frisbee and I said, how fast is that frisbee going? Well, I could determine that based on how fast the plane is going and how fast the frisbee is going relative to the plane. If I have both of those things, I can determine how fast it's going. Okay, what that looks like mathematically, right, would be if I've got 2 points, we'll talk position first, and I got point A, and there's a vector pointed to point A, a position vector pointed to point A, and I got a position vector pointed to point B. Call this R A, and this R B. Okay, so it has those two positions. Right? And then there'll be another vector that goes between these two. And we'll call that R A as seen from B. or A relative to B. And the direction of those arrows do matter, right? If I'm going from A down to B or B up to A, right? What those vectors and the signs of those vectors will be different based off of that. Okay, so just be careful of the directions things are going. And so what this is saying is if I want the position of A, I can either go this, just the position of A, or I can go to the position of B and then add on to it the position of A as seen from B. And I can get to the same spot, right? That's how vector addition works, right? I could do that. I could break it up into two different components. This is gonna be, it's really important that you get this. We have some simple problems to do with particles, but where it really is gonna play in, is we're gonna do this a lot in rigid body stuff. You got rigid bodies, we have objects attached to other objects that are long, and we want to keep track of what one end is doing relative to the other end, and it plays in a lot. So this quick little definition is going to be used a lot throughout the semester. Okay, and so that's just vector addition, right? If I want to get to A, I just go through here and then up to there. Okay, and so let's define some of these terms. Right, RA and RB are the positions of A and B relative to the origin. Okay, sometimes that's called the absolute position. The absolute positions is that RAs and RBs. And then I always say this one here, I call this the position of A as seen from B, or relative to B. You can say it either way. In this class, I always just say, it's to me, in my simple brain, it works best to say like, this is what A looks like from B. This is A seen as seen from B. And again, that's different than what B looks like from A, right? And so the order of those make a difference. A is seen from B or B is seen from A, okay? I say as seen from, okay? And we just mentioned this before. Graphically, we said this. So if I was to calculate RA, I could say it's the position of B plus the position of A as seen from B. Okay? So if I just took the derivatives of that position right there, I could determine the velocity. Basically, it just means that this definition also works for velocity, and it also works for acceleration. Right? So you just take the derivatives of those and it just kind of falls out. Or just keep in mind that velocities and accelerations are vectors as well. And so this vector addition, it's just vector addition is all we're doing here. It applies to both velocity and acceleration. Okay? Oh, shut down my notes here. Okay, so then back up to that plane example. If I wanted that frisbee, according to this, I could say that the velocity of the frisbee, right, is equal to the velocity of the plane, plus, I'll leave that as a curve, I don't know why it's doing that, plus the velocity of the frisbee that's seen from the plane. I don't know why I drew that. It makes sense. I mean, just right, if I was to do this thing, vectors and stuff like that, in our definition, that would make sense. But also just intuitively, if I wanted the velocity of that frisbee, I'd figure out what's the velocity of the plane, and I would add on to it the velocity of the frisbee as seen from the plane, and that would tell me what the overall velocity of that frisbee is when it's on the plane flying around. Okay, questions about that? And that's it. That's all we have for these relative velocities and accelerations. We'll see you in an example here shortly, okay, on how to apply that, okay? And we'll go from there. So then this is key to do. So if you're like back to the if you're using some sort of solution manual or even in the back of the book, right, the answer to 13.164 in your homework is incorrect. The right answer is this answer. Okay, I think the book has maybe both are negative. The I and the J are both negative, but this is the right answer. There's some confusion on that last time. I was like, oh, it's the wrong answer, and then I gave this one, and then but this is the right answer. Is what I have. I hate it when the back of the book gives wrong answers for practice problems, because here you are trying to learn the subject, and then you keep getting the right answer, but then the back of the book's the wrong answer, and you're trying to convince yourself why it is that it's the wrong. In this case, they absolutely got it wrong. Acceleration A is seen from B is 200 in the I minus 200 in J feet per second squared. Okay. All right, so if we have an airplane pointed due north with a wind speed of 560 miles per hour, so the velocity of the plane as seen from the wind is 560 miles per hour. Wind is 60 miles per hour at 30 degrees as shown. There is nothing being shown at this point. So here's my airplane. It's pointed due north. Okay, and it's got, the wind is traveling at a certain velocity. It's doing this. And this angle here is 30 degrees. Okay, and what it asks us to find is the ground speed and course. The course is the direction. Ground speed is how fast it's going, and then the course is which direction is it actually traveling, right? It's pointed north, but the wind is moving. So there's some relative motion stuff going on, right? It's pointed north, it's going 560 miles an hour relative to the wind, and then it's drifting off to the side. So where is it actually headed? Okay, so we'll come back to our definition of velocity in relative motion. VA is equal to VB plus VA is seen from B. So V plane, that's what I want, is the velocity of the plane, is equal to V wind plus velocity of the plane as seen from the wind. Okay, these are vectors. Okay. The velocity of the plane is seen from the wind. Seen from the wind in this particular example is 560 in the J direction. Miles per okay, it's pointed due north. Right, so relative to the wind, it's pointed due north, and so that's in the J direction. And it's traveling 560. It's the plane is seen from the wind. Someone told me once that this airplanes have this little sensor on the front, the little cone thing that can. Any pilots in here? So I talk as if I know what I'm talking about, and then like there's sometimes there's a pilot, and they're like, actually, that's not what happens. But now I can say whatever I want. You guys don't know. Okay, so I think that there's a little cone on the front of the plane. This is what a guy told me. And then that little cone can measure the wind kind of going through it, and you can come up with a velocity based off that. I doubt it gets used too much anymore because now we got GPS and all these other things, but I'm sure it still has it there just in case. Okay, so you can tell how fast you're going relative to the wind. Right? So that's 560 in the J. Right? That's the plane as seen from the wind. Then the velocity of the wind, is equal to, right? They said it's going at 60 miles per hour. So it is 60 miles per hour, and then its direction is just going to be the components in the I and the J. Cosine 30 in the I plus sine 30 in the J. Right, so it's just these components over here, right? This guy and this guy. I should probably label my axes. That's the X, that's the Y. The way that I'm defining this. And just break it into just two components. This is just a vector problem. I could do that. I'll break it into the I component and the j component. Okay, so then my velocity of my plane, is equal to velocity of the wind, 60 times cosine 30 in the I, plus sine 30 in the j, plus 560 in the j. Right, and then you add the light components. You can't add an I to a j, but you can add two j's together, right? Just some vector math. Okay? And what you get here is equal to 51.96 in the I plus 590 in the j miles per hour. Okay, that's its velocity vector. So because it's right, it's basically doing this, right? It's pointing north, but then it's like, but it's drifting as it's going because the wind is drifting. Okay.
What happened to
Yeah.
the 60 sine 30 in the j?
The 60 sine 30 in the j. It went in here, see?
30 is just that.
Yeah, that ends up being 30. 60 sine 30 is a half.
Okay.
Right? Yeah, so then yeah. I just have to do the math.
I read it as the same numbers for some reason.
Yeah. So the bottom one is 590. Yep. Good question. Okay. I'm going to leave it like that. Technically, it asks for the ground speed and course, which is like the angle off the north. I'm not going to do that. This is basically it. Okay. This is more involved. I just want to make sure I have enough time to do this. Okay. So now we have some weird stuff going on here. Okay. I've got particle A, I guess it's two cars. So I got a car traveling around in a circle, right, at a constant speed on the circular track. And then there's A and B both have constant speeds and they have on different radiuses, or radii, okay? And we are asked to find, should this be VB right here? VA is 36, so VA is 36, VB is 45, and then it asked me to find the velocity of B is seen from A, and the acceleration of B is seen from A. And what that's saying is what would it look like if I was on A, and I was looking back at B, what would it look like it was doing? Right? How would it look like it's accelerating stuff? Right? This is going to be a case, so this is going to be a case that polar coordinates are going to work out great for us, right? Because these things are traveling around in circles, so polar coordinates or normal tangent would work, but we just got to with polar, so we'll do it with polar, right? So I can figure out the velocity and accelerations of A and velocity accelerations of B. But then the problem is, it's saying how is one related to the other? And where the difficulty becomes is if I do it in polar coordinates, I'm going to have velocity of A in velocity of A and acceleration of A in this direction and this direction, right? But then B down here, its coordinates are going to be going this way and this way, right? Its ER and E theta are in different directions, right? So I can't just add the ERs and E theta together because now is a case where there's one down here doing this and there's another one up here doing this. I can't just add them together, right? So I need to get them in the same coordinate system first. Once I put them in the same coordinate system, then I can add them. Okay, and so this is a little bit more difficult problem because I have to do it I'm going to do it polar coordinates to begin with. Then I'm going to switch them over to Cartesian coordinates, and when they're both in Cartesian coordinates, then I can add them and subtract them. Okay, there's other ways to think of it too. I think this is the most straightforward way to do it. You can think of it in terms of like, oh, they're like this, and I can figure out what components of this are in that, and what we're just going to do it the way that we've kind of laid out for ourselves. Okay. All right, so just really quick, just to kind of lay out where we're headed, right? We determined this before. The velocity of B was equal to the velocity of A plus the velocity of B as seen from A, right? That was our definition from before, right? But in this case, what it's asking for is the velocity of B as seen from A. So I could just rearrange this equation a little bit and say the velocity of B as seen from A is just going to be the velocity of B minus the velocity of A. Okay, same thing will play out for accelerations. AB is seen from A, acceleration of B minus the acceleration of A. I'm kind of just rearranging that equation that we derived earlier. Okay, that's where we're headed, right? So I need to get velocity of B and the acceleration of B and the velocity of A and the acceleration of A. Okay, so let's do car A first. Okay. What is it doing? Again, polar coordinates going to work out best for us at the beginning. The velocity of A in polar coordinates of something traveling around in a circle is just going to be r omega in the e theta direction. Or VA in the e theta direction. In this case, the velocity, calling it velocity VA, makes it easy. It's just the velocity. And there's the E theta is going that way, and ER is going that way for car A, right? And so our E theta is going to go that direction, and that's just going to be our velocity in the E theta direction. Or R omega, they're all related to each other. We talked about that before, right? In this case, it's easier to call this velocity of A in the E theta direction, right? So this is going to be equal to 36 in the E theta direction, and that's feet per second. Okay. Okay. And that's the velocity. Let's talk acceleration. Acceleration of B. Acceleration of B is equal to R alpha in the E theta direction minus R omega squared in the ER direction. These are just coming from up above. A couple pages before, we had polar coordinates traveling in a circle. You have an R alpha in the E theta direction minus R omega squared in the ER direction. R alpha in this case, these things are traveling at a constant velocity, so there is no R alpha term. So that goes to 0. Right, this can be written a couple different ways. You could do it R omega squared, which is also equal to VA squared over RA. And we talked, there's two, we wrote these down before too. They could be, we could talk about things in terms of R omega squared or VA squared over R. Either one of those things work. Okay, in this case, we know the velocity, so that makes more sense. So this ends up being equal to negative 36 squared, and 1250 is the radius of A. And that would be in the ER direction. Okay, that's velocity A and the velocity of A and the acceleration of A. Okay. So there's just an acceleration back. So this one's got no acceleration that way, but an acceleration back towards the center of that V squared over R. Okay? All right. Now we'll look at car B. Car B. Again, in polar coordinates, my VB vector is just going to be VB in the E theta direction. It's going to be equal to 45 in E theta direction. Feet per second. Okay. Acceleration of B is going to be equal to R alpha in E theta direction minus VB squared over RB. Right.
again, alpha is equal to 0. It's constant velocity, so that's equal to 0. And then this is equal to negative 45 feet per second. Oh, sorry. Getting ahead of myself. 45 squared all over 1,200 feet per second squared. Oh, and then in the, well, that's directions. Oh man, I'm falling apart here. This is in the ER direction. This is in the ER direction. Okay. All right. So this is the point now. You gotta be careful, right? Before, when we could just add and subtract vectors, right? We did i's and j's just in that previous problem. We just like the I terms, and then you like the j terms, and they come together, right? But in this case, we can't do it. You'll want to do it. You're like, well, this is 36 in the e theta. So I got if I want my velocity of b as seen from A, well, this is 36 in the e theta, and I'm just going to subtract minus 45 in the e theta direction. The problem is both of their e thetas. This e theta down here, this e theta is not the same as this e theta, right? Because one e theta, one's going like this and this, and the other one's going like this and this, right? And so this is the one e theta, and that's the other e theta. They don't line up. So you could do a little bit of math at this point. You could look at it and like, oh yeah, I can figure out what components are this way and what components are that way. Or you can use the definition that we had before. We'll put them both in Cartesian coordinates, and once they both get into Cartesian coordinates, then we can just add and subtract, because now they'll have the same fixed coordinate system, okay? All right, so let's do that. Let's go over to Cartesian. I like this problem because we get to use our couple definitions that we had before, right? For how you make that transformation. So VA was equal to 36 in the e theta direction. And I'm going to cheat here. I'm going to go up here. I'm going to grab this. If you want to convert between the two, we had this. Right. You could just reference up above, but this is, I gave this to you before. Okay? And the way you use this is just every time you see an e theta in this conversion, you just write this. Right? So you don't have to think too much. You don't have to look. If you looked at the geometry, you could figure it out. You can make it work. Say, well, if I could figure out e theta, I can figure out what components going this way and what components that way, or just use this definition that we made from before, right? So at this point, this could be equal to 36, and so instead of e theta, I'm going to write this. I'm going to write this guy right here. Negative sine, and the angle that we have is 25. If you look up above, that angle is 25. So 25 in the I plus cosine 25 in the j. Okay. You could do the same for VB, right? Or we can do this by inspection. We'll just look at what's happened with VB. Right. If I'm looking at VB, this is VB right here. That's already kind of lined up with the coordinate system. This is going to be VB. There's ER, there's E theta. So E theta is just in the J direction. It lines up in that direction. That being said, if you use this little substitution, that same substitution, and put in your angle as 0, you get the same answer. Okay? It just lines up in the J. Or you can see it too. So this is going to be 45 in the J direction. So this is what my velocity of A is in Cartesian coordinates. This is my velocity of B in Cartesian coordinates. Right? Do the same thing with accelerations. Acceleration to A is equal to negative 36 squared over 1250. Well, I didn't calculate that out. I was being lazy. ER. And that's going to be negative 36 squared over 1250. Right? And then I now, instead of writing ER, I just write this. Okay? Let's write that. ER would be cosine 25 in the I plus sine 25 in the J. Okay, that is acceleration of A in Cartesian coordinates. And then B, AB again is the ER lines up in the I direction. So this is negative 45 squared over 1200 in the ER direction. That's negative 45 squared over 1200 in the I direction. Okay, once I get them all in Cartesian coordinates, now I can just add and subtract them because everything is relative to the same reference frame, the same coordinate system. All right, and I skip lots of math steps. I'll tell you what I got for the answer. It'd be good exercise when you're studying for the exam, making sure you can get this. Substituting in and making sure you know how to do vector math. Velocity of B is seen from A. The magnitude of it, because it asks for the magnitude. You put bars on the outside, it means magnitude. You get that of 19.6 feet per second. And then acceleration, as seen from A. Magnitude, right? The magnitude square root of the sum of the squares of the components is 0.87. Okay. So at that point, just to kind of make it clear, right? We just did that with it. To get B as seen from A, I took the velocity of B minus the velocity of A, right? And then in the same coordinate system, you could do that. So this J is the same as that J right there, and you carry out the math and do the square of the sum of squares, and you get the answer that I have down below. Okay? Questions about that one? Yes, Nate Dog.
Under car A, when you wrote the acceleration, was that supposed to be acceleration of A or B?
Well, I wasn't done yet, Nate Dog, but let's go up and see what I maybe did. What did I do?
So under car A.
Oh, I said AB. You just can't read my writing, Nate Dog. This is A. Yeah. It was just bad handwriting. I did absolutely write B, and I should have written A. Yeah. But earlier I was like, I hate when the book makes mistakes. You're trying to learn it, and then the book's like, here I am making mistakes and writing in an illegible manner. And so, okay. So that is the end of this section in notes, okay? So for Wednesday's class, print out the next section if you haven't done so already, right? Or get that thing, or get it ready. Let's just kind of look to see where we're headed while we're sitting here. That is structural dynamics, that is not aerodynamics. Okay, this is it. I mean, honestly, when I get to I always have a sigh of relief when I get done with that, the kinematics. Do the kinematics go away? Absolutely not, right? We're still gonna be doing kinematics. It's just, we're gonna start from one step back, right? And because we're starting one step back, a lot of the emphasis goes on that, and that one step back is coming up with that acceleration equation. So we're gonna take a little step back onto that side. And because of that, then the integrals and stuff like that kind of lessen because you spend more of your time working on this, okay? So this is where we're gonna relate forces and motion, okay? And so the first thing that we're gonna write down right here, we got 5 minutes. No, I don't want to. It's Monday. I'm not doing it. I'm not starting. Okay, F equals ma. We're going to write down some of the forces as mass times acceleration, right? And then I'm going to lay out this nice, sick way. We're going to do it in Cartesian coordinates. Then we're going to do it in normal tangent coordinates. Then we're going to do it in polar coordinates, okay? But we're going to draw free body diagrams, just like you did in, right? I mean, that's where we started in statics. We drew a free body diagram, applied our loads to it, and then we summed the forces, and we said that they're equal to 0. In this case, though, we're going to sum the forces. We're going to draw a free body diagram, sum the forces. The forces in the x are going to be mass times acceleration in the x. Sum of the forces in the y, mass in the y. right, times the A and the Y, and then sum of the forces in the Z is going to be mass and acceleration Z. Just as simple as that, okay? So we're going to draw these little free body diagrams, and then out of that, we can get our acceleration equations. Once we get the acceleration equation, we can go. And we're going to have a nice, beautiful solution procedure where we draw, I have step by step, figure out the mass properties, sum the forces, draw a free body diagram, then sum your forces in the X, sum your forces in the Y, sum your forces in the Z, and then do your kinematics, because there's still going to be kinematics involved, and then we're going to solve. And we're just going to say that every time. Types of problems we're going to be solving, right? This should look familiar. We did a very similar problem like this, except for we started with the acceleration equation. This time we're not. We're going to start with this. We're going to sum our forces, set those equal to mass times acceleration, and then solve for this thing using methods. And there'll be some kinematics involved and stuff in that as well, right? Here's lots of weird contraptions in dynamics. Lots of weird contraptions. In this case, we're going to have this little block that's sitting on an inclined plane. I'm going to pull down with a force P, and then you can imagine if I pull down a lot, then that thing's going to accelerate up to the right, right? If I don't pull enough, then it's going to accelerate down to the left. And so we're going to be messing around with that system, and using this method that we had with free body diagrams will help us do that. Then we're going to do another problem. Then we're going to do this different coordinate system, because that coordinate system we used before, again, there's going to be certain types of problems where certain coordinate systems are going to work better than others. Then we're going to do polar coordinates, F equals ma, and then we'll be done with that. Then we're going to do work energy, and then we'll do impulse momentum, and then we're done with particles. Okay, that's a ways out, and then we're getting into real stuff. Okay, so then again, an exam next Friday. It's going to be, I'm pretty sure it's one kinematics problem and one F equals ma problem. Okay, is how I structure it. It's just two problems, me versus you, 50 minutes in class. We're gonna do it. Okay, then the next exam will be work energy and impulse momentum in particles, and then we move on to 2D rigid body, and then we kind of take the same path. Yeah.
Are all the kinetic equations going to be given?
You get a note sheet. You get a cheat sheet, 1-page cheat sheet. Okay, so that's so no. But you get to write it down. Yeah. Cool vids. Yeah.
Are you going to give us recommended problems to work on?
Yeah, so then the week leading up to it, next week, I'll give you 2 old exams, okay? And then you could do it. And then I think usually either the night before or 2 nights before, I'll do a review session, okay? And so I got to find a room and stuff, and then I basically what I'd like to happen is I give you the 2 example problems a couple days before, and then that review session is I'm just going to do the 2 example problems in front of you guys, right, or with you guys, I guess. Yeah.
So on syllabus, you have a test on 27th. Are you?
Is that not?
Yeah.
Is that way? Oh, we got to. Well, I'm scaring you guys for no reason. It's probably that. Yeah. I was a little concerned because like, are we going to make it through all the F equals ma? I didn't think we were gonna. So. Scratch that. Well, you guys can tell me this. One time, this is a true story. One time, I messed up. I was lecturing to the students, and I was like, I was telling them, I was like, all right, so because they used to have the exams in the evening. They don't let us do that anymore. But then they had the exam. I was like, oh, so when you guys do the exam this evening, you could do this. I messed up. It was actually the next evening, right? But I said this evening, which scared the class, because the whole class goes, you know, I was like, what? And they go, the exam, you said the exams this evening. And I go, the exams this evening? And they scared me, like, I was like, I thought it was tomorrow. They scared me back. So it was pretty, and I swear to God, it was 100% true. I scared everybody, they all gasped, and then they said it back to me, and then I gasped. And so it was interesting. Yes, someone had a question over here, yeah.
So is the homework the week of the exam gonna be a little lighter?
Yes. It's supposed to be. I gotta look. I'm always, my schedule's off here. Yeah. I thought it was next week, but it must be the following week. We'll see. But I thought I had light next week. But I must not. I must not have light next week. Okay. But I will. I have structured it this way so it's lighter on the exam week. So. Okay. Cool. Break.